Electromagnetic induction. Describe how voltage is induced in a coil of wire. State and explain Faraday's law. Describe how a generator works. Describe how a magnetic field affects a moving charge. Describe how a transformer works. Explain why almost all electrical energy is sold in the form of alternating current. Explain how an electric field creates a magnetic field. Describe electromagnetic waves. Magnetism can produce electricity, and electricity can produce magnetism. The discovery that an electric current in a wire produced magnetism was a turning point in physics and the technology that followed. The question arose as to whether magnetism could produce an electric current in a wire. In 1831, two physicists, Michael Faraday in England and Joseph Henry in the United States, independently discovered that the answer is yes. Until their discovery, the only current-producing devices were voltaic cells, which produce small currents by dissolving expensive metals in acids. These were the forerunners of our present-day batteries. The discovery of Faraday and Henry provided a major alternative to these crude devices. Their discovery was to change the world by making electricity so commonplace that it would power industries by day and light up cities by night. Can you create an electric current without a battery? Use two lengths of wire to connect two galvanometers. Shake one of the galvanometers while watching the needle of the other meter. Now reverse the roles of the galvanometers by shaking the galvanometer that was originally stationary. Observing. Describe the reading on a stationary galvanometer as the other galvanometer is shaken. Predicting. What would happen if you moved a magnet through the wire loops connecting the galvanometers? 3. Making generalizations. How could you use mechanical motion to power an electrical device? 37.1. Electromagnetic induction. Faraday and Henry both made the same discovery. Electric current can be produced in a wire by simply moving a magnet into or out of a wire coil. No battery or other voltage source was needed. Only the motion of a magnet in a coil or in a single wire loop, as shown in figure 37.1. They discovered that voltage was induced by the relative motion of a wire with respect to a magnetic field. The production of voltage depends only on the relative motion of the conductor with respect to the magnetic field. 37.1. When the magnet is plunged into the coil, voltage is induced in the coil and charges in the coil are set in motion. Voltage is induced whether a magnetic field of a magnet moves past a stationary conductor or the conductor moves through a stationary magnetic field as shown in figure 37.2. The results are the same for the same relative motion. The amount of voltage induced depends on how quickly the magnetic field lines are traversed by the wire. Very slow motion produces hardly any voltage at all. Quick motion induces a greater voltage. The greater the number of loops of wire that move in a magnetic field, the greater are the induced voltage and current in the wire as shown in figure 37.3. Pushing a magnet into twice as many loops will induce twice as much voltage. Pushing it into 10 times as many loops will produce 10 times as much voltage, and so on. Figure 37.2. Voltage is induced in a wire loop whether the magnetic field moves past the wire or the wire moves through the magnetic field. Figure 37.3. When a magnet is plunged into a coil of twice as many loops as another, twice as much voltage is induced. If the magnet is plunged into a coil of 3 times as many loops, then 3 times as much voltage is induced. Does it seem that we get something energy for nothing by simply increasing the number of loops in a coil of wire? We don't. Work is done by pushing the magnet into the loop. That's because the induced current in the loop creates a magnetic field that repels the approaching magnet. For example, in 37.4a, the north pole of the bar magnet is pushed towards a single loop. The current induced in the loop produces a magnetic field that repels the approaching bar magnet. We see that in figure 37.4b. When the magnet is pulled away from the loop, the induced current produces a magnetic field that attracts the receding bar magnet. Both cases require work input. 37.4a, current induced in loop produces a magnetic field suggested by the imaginary yellow bar magnet, which repels the approaching bar magnet. B, when the bar magnet is pulled away from the loop, the induced current is in the opposite direction and produces a magnetic field that attracts the receding magnet. If you try to push a magnet into a coil with more loops, it requires even more work, as shown in figure 37.5. The law of energy conservation applies here. In figures 37.3 and 37.4, the force that you exert on the magnet multiplied by the distance that you move the magnet in your input work. This work is equal to the energy expanded or possibly stored in the circuit in which the coil is connected. If the coil is connected to a resistor, for example, more induced voltage in the coil means more current through the resistor and means more energy expenditure. The amount of voltage induced depends on how quickly the magnetic field changes. Very slow movement of the magnet into the coil produces hardly any voltage at all. Figure 37.5. It is more difficult to push the magnet into the coil with more loops because more current flows and the coil generates a stronger magnetic field that resists the motion of the magnet. Quick motion induces a greater voltage. It doesn't matter which moves, the magnet or the coil. It is the relative motion of the coil with respect to the magnetic field that induces voltage. It so happens that any change in the magnetic field around the conductor induces a voltage. The phenomena of inducing voltage by changing the magnetic field around a conductor is electromagnetic induction. Concept check. How can you create a current using a wire and a magnet? 37.2. Faraday's law. Faraday's law describes the relationship between induced voltage and rate of change of a magnetic field. Faraday's law states that the induced voltage in a coil is proportional to the product of the number of loops, the cross-sectional area of each loop, and the rate at which the magnetic field changes within those loops. Voltage is one thing, and current is another. The amount of current produced by electromagnetic induction depends not only on the induced voltage, but also on the resistance of the coil and the circuit to which it is connected. Think, if you push a magnet into a coil connected to a resistor as shown in figure 37.5, you'll feel a resistance to your push. For the same pushing speed, why is the resistance greater in the coil with more loops? Simply put, more work is required because more turns mean that more voltage is induced, producing more current in the resistor and more energy transfer. You can also look at it this way. When the magnetic fields of two magnets, electro or permanent, overlap, the two magnets are either forced together or forced apart. When one of the fields is induced by motion of the other, the polarity of the fields is always such as to force the magnets apart. This produces the resistive force you feel. Inducing more current in more coils simply increases the induced magnetic field and thus the resistive force. For example, You can plunge a magnet in and out of a closed rubber loop and in and out of a closed loop of copper. The voltage induced in each is the same, providing each intercepts the same number of magnetic field lines, but the current in each is quite different. A lot in the copper, but almost none in the rubber. The electrons in the rubber sense the same electric field as those in the copper, but their bonding to the fixed atoms prevents the movement of charge that occurs so freely in the copper. Concept check. What does Faraday's law state? 37.3. Generators and alternating current. One way to generate a current is to plunge a magnet into and out of a coil of wire. As the magnetic field strength inside the coil is increased, magnet entering, the induced voltage in the coil is directed one way. When the magnetic field strength diminishes, magnet leaving, the voltage is induced in the opposite direction. The greater the frequency of field change, the greater the induced voltage. The frequency of the induced alternating voltage equals the frequency of the changing magnetic field within the loop. Rather than moving the magnet, it is more practical to move the coil. Figure 37.6. A simple generator turns mechanical energy into electrical energy. Voltage is induced in the loop when it is rotated in the magnetic field. This is best accomplished by rotating the coil in a stationary magnetic field, as shown in figure 37.6. A machine that produces electric current by rotating a coil within a stationary magnetic field is called a generator. It is essentially the opposite of a motor. Whereas a motor converts electrical energy into mechanical energy, a generator converts mechanical energy into electrical energy. Simple generators. When the loop of wire is rotated in the magnetic field, there is a change in the number of magnetic field lines within the loop, as shown in the diagram above. Figure 37.7. As the loop rotates, there is a change in the number of magnetic field lines it encloses. A. The loop starts by enclosing the maximum number of field lines. B. As the loop rotates, fewer field lines pass through it. C. In this position, the loop encloses no field lines. D. Now the loop encloses more field lines again. E. After half a turn, the loop again encloses the maximum number of field lines. In 37.7a, the loop has the largest number of lines inside it. As the loop rotates, 37.7b, it encircles fewer of the field lines until it lies along the field lines and encloses none at all, 37.7c. As rotation continues, it encloses more field lines, 37.7d, and reaches a maximum when it has made a half revolution, 37.7e. As rotation continues, the magnetic field inside the loop changes in cyclic fashion. The voltage induced by the generator alternates, and the current produced is alternating current. The current changes magnitude and direction periodically, as shown in 37.8. 37.8. As the loop rotates, the magnitude and direction of the induced voltage and current change. One complete rotation of the loop produces one complete cycle in voltage and current. The standard alternating current in North America changes its magnitude and direction 60 complete cycles per second, 60 hertz. Complex generators. The generators used in power plants are much more complex than the model discussed here. Huge coils made up of tiny loops of wire are wrapped on an iron core to make an armature much like the armature of a motor. They rotate in the very strong magnetic field of powerful electromagnets. The armature is connected externally to an assembly of paddle wheels called a turbine. Energy from wind or falling water can be used to produce rotation of the turbine, but as shown in figure 37.9, most commercial generators are driven by moving steam. At the present time, a fossil fuel or nuclear fuel is used as the energy source for the steam. Notes: guitar pickups are tiny coils with magnets inside them. The magnets magnetize the steel strings. When the strings vibrate, voltage is induced in the coils and boosted by an amplifier, and sound is produced by a speaker. Figure 37.9. Steam drives the turbine, which is connected to the armature of the generator. It is important to emphasize that an energy source of some kind is required to operate a generator. Some fraction of energy from the source, usually some type of fuel, is converted to mechanical energy to drive the turbine, and the generator converts most of this to electrical energy. The electricity that is produced simply carries this energy to distant places. Some people think that electricity is a source of energy. It is not. It is a form of energy that must have a source. Concept check. How is a generator different from a motor? 37.4. Motor and generator comparison. In chapter 36, you saw how an electric current is deflected in a magnetic field, which underlies the operation of the motor. This discovery occurred about 10 years before Faraday and Henry discovered electromagnetic induction, which underlies the operation of a generator. Both of these discoveries, however, stem from the same single fact. Moving charges experience a force that is perpendicular to both their motion and the magnetic field they traverse. We will call the deflected wire the motor effect and the law of induction the generator effect. Each of these effects is summarized in figure 37.10. Study them. Can you see that the two effects are related? The motor effect occurs when a current moves through a magnetic field. In the figure, the current is moving to the right, and the magnetic field creates a perpendicular upward force on the electrons. Because the electrons can't leave the wire, the entire wire is tugged upward along with the electrons. In the generator effect, a wire with no current is moved downward through a magnetic field. The electrons in the wire experience a force perpendicular to their motion, which is along the wire. So a current begins to flow. A striking example of a device functioning as both motor and generator is found in hybrid automobiles. Figure 37.10. The figure shows the motor effect and the generator effect. A. When a current moves to the right, there is a force on the electrons and the wire is tugged upward. B. When a wire with no current is moved downward, the electrons in the wire experience a force, creating current. When extra power for accelerating or hill climbing is needed, this device draws current from a battery and acts as a motor to assist the gasoline engine. When braking or rolling down causes the wheels to exert a torque on the device, it acts as a generator and recharges the battery. The electrical part of the hybrid engine is both a motor and a generator. Concept check. How does a magnetic field affect a moving charge? 37.5. Transformers. Consider a pair of coils side by side as shown in figure 37.11. One is connected to a battery and the other is connected to a galvanometer. It is customary to refer to the coil connected to the power source as the primary input and the other as the secondary output. As soon as the switch is closed and the primary and current passes through its coil, a current produces in the secondary also, even though there is no material connection between the two coils. Only a brief surge of current occurs in the secondary, however. Then, when the primary switch is open, a surge of current again registers in the secondary, but in the opposite direction. Figure 3711, whenever the primary switch is open or closed, voltage is induced in the secondary circuit. The explanation is that the magnetic field that builds up around the primary extends into the secondary coil. Changes in the magnetic field of the primary are sensed by the nearby secondary. These changes of magnetic field intensity at the secondary induce voltage in the secondary in accord with Faraday's law. If we place an iron core inside the primary and secondary coils of the arrangement shown in figure 3711, the magnetic field within the primary is intensified by the alignment of magnetic domains in the iron. The magnetic field is also concentrated in the core, which extends into the secondary, so the secondary intercepts more of the field change. When the switch of the primary in figure 3711 is open or closed, the galvanometer in the secondary registers a current. But when the switch remains closed, no current is registered on the galvanometer of the secondary. Why? A current is only induced in a coil when there is a change in the magnetic field passing through it. When the switch remains in the closed position, there is a steady current in the primary and a steady magnetic field about the coil. This field extends into the secondary, but unless there is a change in the field, electromagnetic induction does not occur. If the voltage in a transformer is stepped up, then the current is stepped down. Ohm's law says that increased voltage will produce increased current. Is there a contradiction here, or does Ohm's law not apply to transformers? Ohm's law still holds, and there is no contradiction. The voltage induced across the secondary circuit divided by the load, the resistance of the secondary circuit, equals the current in the secondary circuit. The current is stepped down in comparison with the larger current that is drawn in the primary circuit. The galvanometer will show greater surges of current when the switch of the primary is open or closed. Instead of opening and closing a switch to produce the change of magnetic field, suppose that alternating current is used to power the primary. When the rate at which the magnetic field changes in the primary and hence in the secondary is equal to the frequency of the alternating current. Now we have a transformer as shown in figure 3712. A transformer is a device for increasing or decreasing voltage through electromagnetic induction. 3712, a simple transformer arrangement using an iron core, creates greater current in the secondary coil. A transformer works by inducing a changing magnetic field in one coil, which induces an alternating current in a nearby second coil. A more efficient arrangement for the transformer is shown in figure 3713, where the iron core forms a complete loop to guide all the magnetic field lines through the secondary. All the magnetic field lines within the primary are intercepted by the secondary. Voltage. Voltage may be stepped up or stepped down with a transformer. To see how, consider the simple case shown in 3714a. Figure 3713, the iron core guides the changing magnetic field lines, which makes a more efficient transformer. Figure 3714a. The voltage of 1 volt induced in the secondary equals the voltage of the primary. B. A voltage of 1 volt is induced in the added secondary also because it intercepts the same magnetic field change from the primary. C. The voltages of 1 volt induced in each of the two one-turn secondaries are equivalent to a voltage of 2 volts induced in a single 2-turn secondary. Suppose the primary consists of one loop connected to a 1-volt alternating source. Consider the symmetrical arrangement of a secondary of one loop that intercepts all the changing magnetic field lines of the primary. Then a voltage of 1 volt is induced in the secondary. If another loop is wrapped around the core, as shown in figure 3714C, the induced voltage will be twice as much, in accord with Faraday's law. If the secondary is wound with 3 times as many loops, or turns as they are called, then 3 times as much voltage will be induced. If the secondary has 100 times as many turns as the primary, then 100 times as much voltage will be induced, and so on. This arrangement of a greater number of turns on the secondary than on the primary makes up a step-up transformer. Step-up voltage may light a neon sign or operate the picture tube in a television receiver. If the secondary has fewer turns than the primary, the alternating voltage produced in the secondary will be lower than that of the primary. The voltage is said to be stepped down. If the secondary has half as many turns as the primary, then only half as much voltage is induced in the secondary. So electrical energy can be fed into the primary at a given alternating voltage and taken from the secondary at a greater or lower alternating voltage, depending on the relative number of turns in the primary and secondary coil windings, as shown in figure 3715. 3715, a practical transformer uses many coils. The relative number of turns in the coils determines how much the voltage changes. The relationship between primary and secondary voltages with respect to the number of turns is primary voltage divided by the number of primary turns equals secondary voltage divided by number of secondary turns. Power. It seems that you get something for nothing with a transformer that steps up the voltage. Not so. For energy conservation, always controls what can happen. The transformer actually transfers energy from one coil to the other. The rate at which energy is transferred is the power. The power used in the secondary is supplied by the primary. The primary gives no more power than the secondary uses, in accord with the conservation of energy. If the slight power losses due to heating of the core are neglected, then the power going into the primary equals the power coming out of the secondary. Electric power is equal to the product of the voltage and current. Voltage times current primary equals voltage times current secondary. You can see that if the secondary has more voltage, it will have less current than the primary, or vice versa. If the secondary has less voltage, it will have more current than the primary. The ease with which voltages can be stepped up or down with a transformer is the principal reason that most electric power is AC rather than DC. Figures 3716 shows a common household transformer used today. Notes: transformers convert voltage from high to low, from 120 to 6 volts for your laptop, or from low to high, from 120 volts to 220 volts for your Hong Kong hair dryer. Concept check. How does a transformer work? 3716. This common transformer lowers 120 volts to 6 volts or 9 volts. It also converts AC to DC by means of a diode inside, a tiny electronic device shown in Chapter 34, Figure 3412, that acts as a one-way valve. 37.6. Power transmission. Almost all electric energy sold today is in the form of alternating current because of the ease with which it can be transformed from one voltage to another. Power is transmitted great distances at high voltage and correspondingly low currents, a process that otherwise would result in large energy losses owing to the heating of the wires. Notes: 200 years ago, people got light from whale oil. Whales should be glad that humans discovered how to harness electricity. Power may be carried from power plants to cities at about 120,000 volts or more, step down to about 2,400 volts in the city, and finally step down again by a transformer such as the one shown in figure 3717 to provide the 120 volts used in household circuits. Energy then is transformed from one system of conducting wires to another by electromagnetic induction, as shown in figure 3718. 3717, a common neighborhood transformer, which typically steps 2400 volts down to 240 volts for household and small businesses inside the home or business. The 240 volts can be divided to a safer 120 volts. 3718. Power transmission depends on transformers. Voltage is increased for long distance transmission and then decreased before it reaches your home. The same principles account for eliminating wire and sending energy from a radio transmitter antenna to a radio receiver many kilometers away, and for the transformation of energy of vibrating electrons in the sun to life energy on Earth. The effects of electromagnetic induction are very far-reaching. Concept check. Why is almost all electrical energy sold today in the form of alternating current? 37.7. Induction of electric and magnetic fields. Electromagnetic induction has thus far been discussed in terms of the production of voltages and currents. Actually, the more fundamental way to look at it is in terms of the induction of electric fields. The electric fields, in turn, give rise to voltages and currents. Induction takes place whether or not a conducting wire or any material medium is present. Faraday's law states that an electric field is created in any region of space in which a magnetic field is changing with time. The magnitude of the created electric field is proportional to the rate at which the magnetic field changes. The direction of the created electric field is at right angles to the changing magnetic field. If electric charge happens to be present where the electric field is created, this charge will experience a force. For a change in a wire, the force could cause it to flow as current, or to push the wire to one side. For a charge in an evacuated region, like in the chamber of a particle accelerator, the force can accelerate the charge to high speeds. There is a second effect, which is the counterpart to Faraday's law. It is just like Faraday's law, except that the roles of electric and magnetic fields are interchanged. The symmetry between electric and magnetic fields revealed by this pair of laws is one of the many beautiful symmetries in nature. The companion to Faraday's law was advanced by British physicist James Clerk Maxwell in the 1860s. A magnetic field is created in any region of space in which an electric field is changing with time. According to Maxwell, the magnitude of the created magnetic field is proportional to the rate at which the electric field changes. The direction of the created magnetic field is at right angles to the changing electric field. Concept check. How can an electric field create a magnetic field? Metal detectors linked to technology. Walk through a metal detector at an airport and you're walking through a coil of wire that carries a small electric current. In the opening in the coil there is a magnetic field. Any change in this field is sensed by the coil. If you carry iron into the coil, you change this magnetic field. A changing magnetic field induces a change in the current in the coil. The change sets off an alarm. Computers store data on plastic discs that have been coated with a magnetic material. Magnetic patterns can be applied to the disk by a recording head. Coded electrical pulses that carry information are changed into magnetic pulses and stored on the disk. When a magnetically stored bit of information on the disk spins under a reading head that contains a small coil, the pulses are converted back to electrical signals again. 37.8. Electromagnetic waves. Shake the end of a stick back and forth in still water and you will produce waves on the water surface. Similarly, shake a charged rod back and forth in empty space and you will produce electromagnetic waves in space as shown in figure 37.19. This is because the shaking charge can be considered an electric current. What surrounds an electric charge? The answer is a magnetic field. What surrounds a changing electric current? The answer is a changing magnetic field. What do we know about a changing magnetic field? The answer is it will create a changing electric field in accord with Faraday's law. What do we know about a changing electric field? 37.19. Shake a charged object back and forth and you produce electromagnetic waves. The answer is, in accord with Maxwell's counterpart to Faraday's law, the changing electric field will create a changing magnetic field. An electromagnetic wave is composed of oscillating electric and magnetic fields that regenerate each other. No medium is required. The oscillating fields emanate, move outward from the vibrating charge. At any point on the wave, the electric field is perpendicular to the magnetic field, and both are perpendicular to the direction of motion of the wave, as shown in figure 37.20. 37.20. The electric and magnetic fields of an electromagnetic wave are perpendicular to each other. Speed of electromagnetic waves. How fast does the electromagnetic wave move? This is a very interesting question, and in the history of physics, a very important one. If you ask how fast a baseball moves, or a car, or a spacecraft, or a planet, there is no single answer. It depends on how the motion got started, what forces are acting, and how fast the observer is moving. But for electromagnetic radiation, there is only one speed, the speed of light. No matter what the frequency of wavelength or intensity of the radiation, this remarkable constancy of the speed of propagating electric and magnetic fields was discovered by Maxwell. The key to understanding it lies in the perfect balance between the two kinds of fields that must exist if they are to propagate as waves. The changing electric field induces a magnetic field. The changing magnetic field acts back to induce an electric field. The wave is continually self-reinforcing. Maxwell's equation showed that only one speed could preserve this harmonious balance of fields. If, hypothetically, the wave traveled at less than the speed of light, the fields would rapidly die out. The electric field would induce a weaker magnetic field, which would induce a still weaker electric field, and so on. If, still hypothetically, the wave traveled at more than the speed of light, the fields would build up in a crescendo of ever greater magnitudes. Clearly a no-no with respect to energy conservation. At some critical speed, however, mutual induction continues indefinitely, with neither a loss nor a gain in energy. From this equation of electromagnetic induction, Maxwell calculated the value of this speed, this critical speed, and found it to be 300,000 kilometers per second. To do this calculation, he used only the constants in his equation determined by simple laboratory experiments with electric and magnetic fields. He didn't use the speed of light, he found the speed of light, nature of light. Maxwell quickly realized that he had discovered the solution to one of the greatest mysteries of the universe, the nature of light. If electric charges are set into vibration with frequencies in the range of 4.3 times 10 to the 14th to 7 times 10 to the 14th vibrations per second, The resulting electromagnetic wave will activate the electrical antennae in the retina of the eye. Light is simply electromagnetic waves in this range of frequencies. The lower end of this frequency range appears red, and the higher end appears violet. Maxwell realized that radiation of any frequency would propagate at the same speed as light. This radiation includes radio waves, which can be generated and received by antennas, as shown in figure 3721. A rotating device in the sending antenna alternately charges the upper and lower parts of the antenna positively and negatively. 3721. Electromagnetic wave emanation by a sending antenna and reception by a receiving antenna. Successive views A through I show how acceleration of the charges up and down the antenna transmit electromagnetic waves. Only sample electric field lines of the wave are shown. The magnetic field lines are perpendicular to the electric field lines and extend into and out of the page. The charges accelerating up and down the antenna transmit electromagnetic waves. When the waves hit a receiving antenna, the electric charges inside vibrate in rhythm with the vibrations of the field. On the evening of Maxwell's discovery of the nature of light, he had a date with a young woman he was later to marry. Notes: at only one speed will the linkage between electric and magnetic fields be in perfect balance, with no gain or loss of energy, exactly the speed of light. While walking in a garden, his date remarked about the beauty and wonder of the stars. Maxwell asked how she would feel to know that she was walking with the only person in the world who knew what the starlight really was, for it was true. At that time, James Clerk Maxwell was the only person in the world to know that light of any kind is energy carried in waves of electric and magnetic fields that continually regenerate each other. Concept check. What makes up an electromagnetic wave? Cellular field technician, physics on the job. Wireless communication through such devices as cellular telephones and pagers depends on communication towers maintained by cellular field technicians. Signals carried by electromagnetic waves are transferred from one tower to the next. The Federal Communications Commission, FCC, determines the frequency of the waves allowed at each tower. Cellular field technicians use physics to analyze or alter the electromagnetic waves coming into a receiver or being sent out by a transmitter. Cellular field technicians are employed by companies that maintain cellular communications towers. Is ELF radiation dangerous? Science, technology, and society. We live in fear of the unsensed. Anything that exists or is imagined to exist yet escapes detection by our five senses is often a source of fear. Many people fear radiation. Some is hazardous and some is not. No one doubts the hazards of radiation from some nuclear reactions, and no one seriously fears the low-frequency radiations of AM radio. But in recent years, a series of books and magazine articles have fanned the flames of public fear by claiming that the extremely low-frequency ELF radiation of some common 60 Hz electric power causes certain forms of cancer. Is this claim true? Some activists say yes, although the scientific consensus is that is just one of many health scares that has no basis. Careful studies have not substantiated the claimed risk. Bioscientists point out that the electric fields due to power lines at the location of a cell in the body are thousands of times smaller than those due to the normal electrical activity of nearby cells. They also point out that the cancer rates have remained constant or fallen over the last 50 years, with the exception of rising cancer rates due to smoking. Yet during this time, exposure to ELF radiation has increased tremendously. More detailed analysis of the studies that prompted the controversy shows no link between ELF and cancer. Critical thinking. Suppose you're a scientist and you find uncertain evidence that some common foods, tomatoes for example, may be a serious health risk. What responsibility would you have to make your findings known to the general public? If you stress the uncertainty of your findings, perhaps no one will listen. Should you then make sensational claims, even unsupported, to get people's attention? Summary: electromagnetic induction. Electric current can be produced in a wire simply by moving a magnet into or out of a wire coil. Faraday's law states that the induced voltage in a coil is proportional to the product of the number of loops, the cross-sectional area of each loop, and the rate at which the magnetic field changes. A generator converts mechanical energy into electrical energy. Moving charges experience a force that is perpendicular to both their motion and the magnetic field they traverse. A transformer works by inducing a changing magnetic field in one coil while inducing an alternating current in a nearby second coil. Almost all electric energy sold today is in the form of alternating current because of the ease with which it can be transformed from one voltage to another. A magnetic field is created anywhere an electric field changes with time. An electromagnetic wave is composed of oscillating electric and magnetic fields.